Yeah, woohoo! Well, hey, next Monday will be more exciting, right? Yes. Exactly, because you won't be here. Hopefully you'll be doing something that you enjoy. Of course. I'm sure some of you enjoy being here, right? Somebody? All right, good. All right. Well, today and Wednesday, I hope you'll find very interesting. We're going to start Special Relativity, Chapter 35. And this can go either way. Some people are like totally confused by this stuff, and others like, oh, yeah, and think it's extremely cool. You have enough physics under your belt now to appreciate it. I mean, not fully. We're not going into quantum mechanics and all that. But you've probably all heard of special relativity and Einstein, and so I want to share it with you. It's in the textbook. I like some of the animations he has. One of them's kind of cheesy, but that's all right. It helps in teaching. Do you guys have any questions before I ask you a few clicker questions on projectile motion? While you're thinking, let's see. So Monday and Wednesday will be Chapter 35, and this is the last chapter in this unit before we have another exam. This Friday we'll review momentum, energy, projectile motion, and relativity. And then the next class we'll have a test, which won't be next Monday because it's a holiday. It'll be the following Wednesday. This homework on Chapter 10 and 35, projectile motion, relativity, will be due Friday night. Not Sunday, Friday night. That's so you can enjoy your weekend or use it to study in theory. Just think, any questions? It's okay if you don't. I just want to ask. All right, get your clickers out. And we'll see how we do. It's 10, 14, yeah, that one. I'm in the wrong program. There's the session ID. You can log in and start answering without air resistance for a projectile. Its horizontal acceleration is? Let's see. That was you. You can still answer. I'll still get your responses even though you haven't registered yet. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right, over half of you think it's 0. All right. At right angles to G is the next biggest common. Somebody that answered that, tell us why that's the correct answer. Yes?
I just saw it a lot in the book, and so I was like, oh, that has to be right.
Ah, repetition. Saw it a lot in the book. So let's see. We got this projectile, and we're ignoring air resistance to simplify it. Its horizontal acceleration is, okay, here's a projectile. Whoosh. Okay. Tell me, what forces are acting on it when it's in the air? Gravity. Good. In which direction? Vertically. Okay, so that's not it. So it's not G. Okay. What other forces? Acceleration of what? Okay, good. And that's why I repeated this question. Yes, I have to accelerate this to get it up to speed. But once it's in the air and is in a projectile, now, I'm no longer pushing on it. So it's not the force from my hand. Yeah, inertia happens, which is not a force. So my point here is there's no horizontal force. It just keeps moving at whatever speed I got it up to. You're right, I had to exert a force to accelerate it up to that speed. But once it leaves my hand, its horizontal velocity does not change. And if the velocity is not changing, there is no acceleration in the horizontal direction. Does that help?
So the answer is 0?
The answer is the majority. It is 0. Because it's not accelerating, it's not changing its velocity horizontally. It's going to go the same distance each second horizontally. Vertically, it is accelerating, and that'll change. Okay? Go. So the idea here is, let's say at this point, when on the way up, whoosh, by the time it gets back to there on the way down, so the same spot on the way up versus on the way down. It's basically asking you, how's the time compare on the way up to the top versus on the way back down to that point? How does that time compare? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. 76% think B. Yes, it is the same time. Realize if you got a certain velocity up, it decelerates it to 0 in that distance. Takes a certain amount of time. And then it accelerates it still down, so it speeds back up, back to that speed. So yeah, it's the same time up as down. If there was air resistance, what would happen? It would be slower. It'd take longer. Wouldn't go as high. There's additional forces. Yeah. How about if I throw it this way? From its height here, when I threw it, to that same height over there. It's still the same, because vertically, it's no different. All right. Last one, go. Yeah, it took me a while to wrap my head around this one too. I guess that's why nobody's answered yet. Basically, it's a tossed ball. When you ignore air drag resistance, that initial horizontal component of velocity. So initially, if I throw it up that way, the horizontal part, this, compared to when it's at the top, is that first blink. Then if you consider air drag, second blink, how do they compare? Does that help? This is a stumper, I can tell. Its initial horizontal velocity when I throw it. I throw it that way, so it's got an initial horizontal. How does this compare to when it's at the top of its trajectory? That's horizontal component there, with and without air drag. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Some of you aren't voting. There we go. Okay, most of you think B. Good. Good. I was hoping you'd get that, especially after the first two questions. So this initial component, it doesn't change horizontally because there's no acceleration. So it's the same throughout the whole flight in any spot, including the top, if there's nothing to slow it down, right? So that's without air drag. But if you throw in air resistance, that's a force impeding its motion. And so this will get a little smaller throughout the flight as air drag pushes on it to decelerate. So it'll be less in that case. Okay, I have a video I want to show you. To start relativity.
We're used to see things from a particular point of view. That is, from a particular frame of reference. And things look different to us under different circumstances. At the moment, things look
You look peculiar. You're upside down.
no, you're the one that's upside down.
No, you're upside down.
No, I'm not. He's the one that's upside down, isn't he?
Well, let's toss for it.
All right.
Okay. You lose. He's the one that's really upside down. You better come into my frame of reference now.
All right. My frame of reference was inverted from what it usually is. That view of things would be normal for me if I normally walked on my hands.
This represents a frame of reference. Just 3 rods stuck together so that each is at right angles to the other 2. Now I'm going to move in this direction. You see the frame at the same spot on your screen, but you know I'm moving this way because you see the wall moving this way behind me. But how do you know that I'm not standing still and the wall moving? It was the wall that was moving. Now the wall has disappeared, and you have no way of telling whether I am moving or not. But now you know that I'm moving. The point of this is that all motion is relative. In both cases, I was moving relative to the wall, and the wall was moving relative to me.
All motion is relative, but we tend to think of one thing as being fixed and the other thing as being moving. We usually think of the Earth as fixed, and walls are usually fixed to the Earth, so perhaps you were surprised the first time when it was the wall that was moving and not Dr. Hume. A frame of reference fixed to the Earth is the most common frame of reference in which to observe the motion of other things.
Oh, for crying out loud. We'll just do that and stop when I'm done.
This is the frame of reference that you're used to. The frame is fastened to the table. The table is bolted to the floor. The floor is anchored in the building, and the building is firmly attached to the earth. Of course, the reason for having 3 rods is that the position of any object, such as this ball, can be specified using these 3 reference lines. This This reference line points in the direction which we call up, which is a different direction here than it is on the other side of the Earth. And these two reference lines specify a plane, which we call horizontal or level. In this film, we're going to look at the motion of objects in this Earth frame of reference and in other frames of reference moving in different ways relative to the Earth frame. Well, let's look at a motion. This steel ball can be held up by the electromagnet. Now I'm going to open the switch and you watch the motion of the ball. The ball is accelerated straight down by gravity along a line parallel to this vertical reference line.
As you can see, the electromagnet is mounted on a cart that can move. And I'm going to do exactly the same experiment that Dr. Hume did, but this time, while the cart is moving at a constant velocity. The cart is pulled along by a string which is wound around this phonograph turntable, and that pulls it with a constant velocity. When the cart passes this line, the ball is released, as you can see. I'm going to start the cart down at the end of the table so that by the time it gets to this point, I can be sure it's moving with a constant velocity. Now, I want you to watch right here so that you will see the ball falling. I think you can see that the ball landed in exactly the same position that it did before when Dr. Hume did the experiment with the cart fixed. But this time, the ball could not have fallen straight down. Let me show you why. The ball was released at that point. If it had fallen straight down, because the cart moves on and the time it takes to fall, it would have landed back here somewhere. But it didn't. Now I'm going to do the experiment again. And this time, I'm going to let you watch the motion through a slow motion camera, which is fixed here as the cart moves by, the ball will fall, and you can watch in the slow motion camera. I'll show you this again. This time there will be a line on the film so that you can see the path. I think that you can see that the path of the ball is a parabola. But all of this has been in a frame of reference fixed to the Earth. How would this motion look in a frame of reference which was moving along with a cart? Frame of reference like that. Well, so that you can see what it looks like, I'm going to fix this slow motion camera so that it moves with the cart. Like this. I'm going to do the experiment again. And incidentally, I'll start it, and then I'm going to stand here so that when the ball falls, you will have something which is fixed as a reference point. In the moving frame of reference, I think you can see that the path of the ball is a vertical straight line. It looks exactly the same as it did before when Dr. Hume did the experiment with the cart fixed. If we were moving along in this frame of reference and we couldn't see the surroundings, then we wouldn't be able to tell by this experiment that we were moving at a constant velocity. As a matter of fact, we wouldn't be able to tell by any experiment that we were moving at a constant velocity. I'm going to do the experiment once more. And this time, I'm not going to stand here behind the ball as it falls so that you won't have any fixed reference frame. As far as you're concerned, that time, the cart wasn't necessarily moving at all. That time, when you couldn't see the background, then I think perhaps it was harder for you to realize that that you were in a moving frame of reference. The important thing to realize here is that all frames of reference moving at constant velocity with respect to one another are equivalent.
Dr. Ivy showed you what the motion of the ball that was released from the moving car looked like in the Earth.
Okay. This was made in 1960, if you couldn't get an idea. But at least they're trying to be humorous, and it shows it very well. It's called just frames of reference, and that's kind of the key behind relativity. It explains it very well, so I hope you were paying attention. Because the key point, one key point here is all motion is relative. Relative to what? We've already kind of discussed it. Remember when we did this? And you're moving. It has a velocity relative to the board and the table. But if this frame of reference is moving with it, it's more fun to make it crash, then that changes things. Its motion relative to the cart is different. Especially when you go the opposite way. I think it's more drastic. So if the cart's moving to your right and I move to the left, for a while there you can make the cart look like it's not moving at all relative to the table. And so frames of reference are very important. You need to know what motion is relative to. Similarly, like with gravitational potential energy, it needed to be relative to a certain height. This cart has no gravitational potential energy relative to the table. But it does have gravitational potential energy relative to the floor. Because if I knock it off the table, it turns into kinetic energy. Where did that energy come from? It must have had potential energy. So it's all relative. And you need to understand which frame of reference you're in. The problem was back then they thought, and people still think today because it's just natural, that there's one absolute reference frame. Like they mentioned, there must be some way you can always tell which one's moving and which one's not. And the truth is you can't. If you get rid of the background or you trap yourself in a room with no windows or something, you can't see a reference point. Sometimes you can't tell whether you're moving or not. Now, special relativity has to do with what we call non-inertial reference frames. When do you notice inertia? When does that rear its head for matter?
When something moves or when something stops.
Good. I'll take that. When something starts to move or when it stops, which we call a change in motion, acceleration. If something is moving at a uniform velocity, the velocity is constant, it's not accelerating, that's a non-inertial reference frame. And in an amusement park, that would be boring. Because, you guys been on airplane flights? And when there's no turbulence and you're not looking out the window, you can't tell if you're moving. You're cruising at hundreds of kilometers an hour. But you can't tell if you're staying at a constant velocity. So for those reference frames, that's what we're referring to in special relativity. The next chapter, which we're not covering, but you're welcome to read, includes inertial reference frames, where you do change your motion and accelerate. And that's general relativity. It gets even more complicated. But that's the gist behind that. So non-inertial reference frames, if you hear that, it just means they're moving at a constant speed. And so there's no absolute frame of reference you can be in to automatically always know what's going on. You guys have experienced this too. You got the plane flight, but how about you're in a car? Maybe you're not the one driving, you're riding, or in a train, and you're never quite sure because you see out the window something move. Are you moving or are they moving? You always raise your hand if you've had that freaky moment for a split second. You're not quite sure if you're moving forward or backwards or both. That's the idea. It's a reference frame and you're not sure. Because that wouldn't work if you're accelerating. So there's a famous experiment that your book talks about. I think it's right at the beginning. Michelson and Morley, the two guys, they back then thought that, okay, space, surely space is absolute. It's fixed, right? The universe is planted. So we might not be able to tell from one train to another or one car to another, but if we always reference to space, we're good. The bottom line is, no. But they set out to prove that. And so they took light, beam of light, and they sent one this way, and then in the middle, it's split. So it's coming along, and then part of the light went this way, bounced back, and part of the light went this way and bounced back. They came together and went to a detector. So they just kind of split it and came back. And something we haven't covered is they make this interference pattern where there's some bright spots and dark spots. In some places they cancel, in other places they add. And so you get little fringes of light and dark bands, and they're on the order of wavelengths, really, really small. The idea is it was very sensitive to motion and distance. If one of these traveled a different speed or a different distance or a different time, they would see a shift easily in the fringes. So they set it up, floated it in a pool of mercury. That's what I like, to insulate it and make it less wobbly. And then they rode the Earth. The Earth goes really fast. They were basically trying to add the velocities together to see a difference. Because if the Earth is moving that way, the light that goes that way should add up with the motion of the Earth and be less on the way back, right? Versus the one that went perpendicular shouldn't have any difference. But they saw no result. This was the most famous experiment in physics where they failed to see what they set out to see, but that result proved that there's no absolute frame of reference. You guys, to put this more in context, you're on a car moving this way. You're in a train, make it easier. If the train's moving 50 miles an hour that way, and I throw the ball at 10 miles an hour, what's the ball's velocity relative to the train? Train's 50, I throw the ball at 10, I'm on the train. What's the velocity of the ball relative to the train? 10. What's it relative to you? 60. See how they add? And if the train's still going that way at 50, but I throw it 10 this way, what's it relative to you? 40. That's what they were trying to do with light, just a lot faster. It failed. They did not add. The speed of light stayed constant. There was no change. It didn't matter if it was going with the Earth or against the Earth or perpendicular to the Earth. They always got the same value because there was no shift. So what this meant was the speed of light is the same in all reference frames. And we've since proven that over and over and over. But this was the first famous experiment to do that. Their null result, unbeknownst to them, proved it. So, there's two main postulates, assumptions, for relativity. And the special theory of relativity is based on these two things. Yes?
So I have a question regarding
Sure.
wavelength color. For example, we perceive something that's red as going slower, and redshift is something getting farther away, whereas ultraviolet tends to be shorter wavelengths and faster. Is that just simply due to our relative position to what we're observing?
The difference in wavelengths and what we see is not due to reference frame. We're going to cover this, but light is a wave. It's an electromagnetic wave. And waves have a certain wavelength. That's the spacing between bumps. So that's a wavelength. It's vibrating up and down at a certain frequency or a rate, 50 million times a second. It also, so it has a frequency, but it also has a speed, a velocity, how fast the wave actually travels through space. And light travels at a constant speed. We're going to call that c. We use the variable c for the speed of light. Wavelength and frequency changes for different colors. Infrared, red. Red has longer wavelengths and vibrates more slowly. Purple has shorter wavelengths and vibrates more quickly. It has more energy also. But they travel at the same speed. Yes, it is. Yeah, the units of that is like 1 per second. An inverse second. Like cycles per second, revolutions per second. We actually call that, since we're going to cover it, I'll just give it to you now. Another guy's last name, it's a hertz. An inverse second is called a hertz.
So is the velocity the wavelength times the frequency?
Yeah, we're going to do that too. The velocity is the wavelength times the frequency. Which, I'll just tell you now, you know this equation. We've done it. What's velocity to you? What? Say again? Yeah, it's distance over time. Wavelength's a distance and frequency is an inverse second, inverse time. So it's really just distance over time for a wave. And this works for all waves. Water, sound, light, all of those. So yeah, light is a wave. And there you go. There'll be other changes too, but we don't need to worry about those yet. Oh yeah, so I'm writing the 2 postulates here. So given these observations, special theory of relativity, number 1, they write it out all nice in your book. All laws of nature are the same in all uniformly moving frames of reference. That means non-inertial. If you're moving at a constant speed, then all the laws of nature are the same in every frame of reference. This is good. In other words, physics doesn't change. That's not technically accurate, but I'm trying to simplify it here. All the laws we've been learning and all the other laws, they're going to be the same and no matter what reference frame you're working in, if the reference frame's moving in a constant velocity. All the laws of nature we know about are the same for everybody, everywhere, in those reference frames. Good, I hope so. Otherwise, gee, you switch to the train, and now what, there's no gravity? That'd be weird. Or velocity isn't distance over time if you're on an airplane? That would just be weird. That's not what we observe, so that's the first assumption. The second is what we just talked about. C, the speed of light, is a constant. It doesn't change. No matter what reference frame you're in, moving in a uniform speed, everybody will measure the speed of light to be the same. It doesn't have that adding of velocities property we're used to with normal matter. I can't tell you why, but that's what we observed. Given those 2 things, the rest of the chapter are the consequences. What does this mean? Given that, there's some funky results. That's when it gets fun. You've probably heard of a couple of them. Let's see. He said in the video, no experiment can reveal absolute motion. That idea, you can't tell whether you're moving or I'm moving. All motion's relative. You don't add. Got that? Yeah. Did you start to raise your hand over here? Okay. So 1 is we call simultaneity. Simultaneity. It's in your book. It's simultaneous, based off of that, which means at the same time. We're used to dealing with if I turn on a light. All right, here's my mag light. Let's see, this looks about like the middle of the room, left to right. If I cover it, and then in the flash of light, ready? Whoosh, whoosh. Those light waves radiate outward from the flashlight, and they go, one goes this way, one goes this way. They actually go every direction. But if we look at these 2, since light travels at a constant speed, and this distance and that distance are the same, it'll take the same amount of time to reach the 2 walls. So when I go, boom, some finite time later, really fast, the light hits the 2 walls at the same time, simultaneously. But that's in our reference frame. What if you guys took off on a spaceship and were to watch me do this? One of the results based on this is that you might not see the light hit the walls at the same time. You could see that wall, it hit that wall first. Or depending on which way you're moving or how fast you're moving, you could see it hit that wall first. What if I was in the spaceship? You guys stay there in the lecture hall and I zip off near the speed of light and I do it again. Say I'm coming by you this way on a spaceship. And I go, doom. What are you going to observe? Think about it. What are you going to observe? Okay, let's work me out. I'm easier. I'm on the ship. The ship's as big as this lecture hall. I'm coming by and I go, doom. What am I going to see moving with the ship? It'll take longer to get that side? You think they'll be the same? Somebody break the tie.
Is the light moving with you? Or?
Good point. Yes. The light and me are on the ship. And we're going to zip by that way. So this table is on my ship with me. So yeah, boom. But we're all moving in unison together. Think about it. If you were on an airplane, and you did this, do you think it would hit the sides of the airplane at the same time? Yes. So I wouldn't see anything different. I would see the events being simultaneous. The light that goes that way and the light that goes that way will hit the sides of my ship at the same time, if I'm in the middle. But what will be weird is for you guys. If I'm cruising this way, think about it. Okay, light ray goes out. Slow motion, right? Okay, but which way have we moved? In the amount of time it takes for the light to go to here, where am I at now? Yeah, I and the flashlight are over here. But the waves are still right here. They're still expanding. You with me? So it's like, flash a light. Boom. They expand out. By the time they get here, I'm over here. By the time I'm over here, they're a little farther, right? At some point, that side of the ship is going to run into this light wave before this light wave runs into that side. Because the ship's kind of running away from the light this way, but the light wins. It's fast. So to you guys, the events won't be simultaneous. You'll see the light hit that wall of my ship first. And then that one. Does that make sense? Are you following me? This is fun for you Star Trek fans or Star Wars even. I often think about it when the Enterprise is engaged with the Klingons or something and they start shooting. They could totally disagree on who fired first. Right? Oh, well, he started it. No, you started it. Oh, well, the treaty. Who broke the treaty first? That's important. Well, if you guys they're moving relative to each other, they can totally disagree. And both are right. Yeah.
I have a super, super important physics-related question. Original series or next generation?
Which version of Star Trek? Well, this would be true any ships in space, wouldn't it? So any sci-fi thing. Oh, which one? I grew up watching the original, so I think I've seen them all, and I love the new one, the Next Generation. And I recently, in the last year, rewatched them all. So I'll admit I didn't go off on the tangents, Deep Space Nine and Voyager. Well, I didn't like any of them as good as the originals. So, but yeah, that concept's kind of fun. That's what simultaneity is about. So one consequence of all this, because light's a constant in each reference frame, you guys are going to measure that velocity the same as I will. So given the distances, they can occur at different times. And we're both right. It all depends on reference frame. So that's one weird consequence. All right. Before we get into others, despite a difference in measurements, we're going to depend. If you're moving at different speeds relative to each other, are you getting an inkling already that you could measure distance differently than I do? Because to me on this ship, I'm that far away from the wall. And if the light travels this fast, and I'm that far away, it should take yay long to get there, correct? A fixed amount of time. But that time disagreed with your time because you said it got there first, right? So times are different. How do you reconcile the time being different? The distance must be different for you and me too. So space and time, you can get different measurements. We're going to talk about time dilation and length contraction are two results. Who's heard of that before this class? Oh, less than I thought, but a couple of you. Yeah, special relativity, usually what most people hear that freaks them out are that time can slow down. That's time dilation. And lengths seem to contract. Things get smaller if there's a motion relative to reference frames. So, do you see how they're based on this? We're still doing physics the same in your reference frame and my reference frame. We both measure the speed of light to be the same, and these just kind of naturally result. These are thought experiments Einstein did. He built on the shoulders of others who came really close to this. Some of them even said some of the consequences, but they didn't understand it. Einstein was brilliant in that he put all this together and made sense of it. Some of the math was done before him, and it's debatable how much he knew when he came up with this theory or not. But that was what Einstein did. So one comforting thing, though, despite these differences, things can occur at different times. You measure distances different. You think time's moving more slowly than I do, depending. There's one constant, and that's the speed of light. Not only is it, well, it's because it's a constant ratio. So somebody that measures space over time, that has, for light, distance over time, right? Velocity is just distance over time. Velocity, distance over time. They get a value. Well, if there's less space, because you get a different measurement, you're going to have that occur in less time, because the ratio is going to stay constant. C is constant. This speed has to be constant. So that might be one way to help you. When you start reading this stuff and getting confused, just remember that. This ratio is one constant. It's a consistent thing between all these reference frames. It's a unifying factor, if you will. So I have another animation that'll help. Okay, so up here, there's two mirrors in the spaceship. And we're just going to send light up. It's going to reflect off and come back down. It's like a light clock, how long it takes to do that. It travels a certain distance up, travels a certain distance down. You're going to see the light move at the top one up here. In the bottom, I can change the speed, a different reference frame at a constant velocity, so it's a non-inertial reference frame. And the bottom spaceship's going to go to the right at some percentage of the speed of light. What will happen to that light beam from our reference point viewing the spaceship cruise on by? What do you think its path will look like? If you're in the spaceship, what will it look like? You're riding along with the spaceship and the light and the mirrors. What do you expect? Yeah, up, down, because you're all moving together. What if you're outside of the spaceship and the spaceship's moving? What do you see? A curved path, maybe. A parabola, which would be a curved path. Well, let's see. Oh, no. It goes up and down in straight lines. Let's reset it and do it again. Goes up, comes down. The idea here, quickly, is you got two components of velocity now. At any given moment, let's see, try to keep it the same. We got the spaceship moving that way. And the light has a okay, not the scale here, obviously. There. And the speed of light velocity up. So at that moment, it wants to move in that direction. These directions don't change, so yeah, it just goes in a straight line. Then it bounces off, turns around, and comes back down the other way. Because now the ship is still going this way, but light is coming down. So it redirects it. Let's watch it again. Let's go faster. We'll go half the speed of light here. You can see up, down. Watch it again. Which one gets back down first? Which reference frame? The top one. The one where if we were in the spaceship at rest relative to that reference frame, that's what we'd see. Yeah, that occurs first. So you can see simultaneity already going on here. It's not working. The events are not simultaneous. One returns before the other. Okay, so the top one takes less time. But this ratio of space and time has to stay the same, so who's going to cover less space? The top one. Can you see it? It's shorter going up and down than it is if you follow the green line on the bottom. Let me go even faster and make it even more obvious. Boom, the top one's already back down before the bottom frame of reference hit the first mirror. Let's blow this up a little. So here's the values. The ship is moving at velocity v. So in that amount of time to get to the top, from there to the top, horizontally, that's how much distance is covered. Do you see that? Distance is rate times time. So it's just the velocity of the spaceship times the time it took the light to get it to the top. Yes?
Is that the basis for like the twin theory?
Yes. Right after this is the twin paradox, which I guess now will be next lecture. So yeah. And I strongly encourage you to read that before we discuss it, because it'll be confusing for a lot of you. So that distance is its velocity times time. The light is going a different speed up here, right? But it's the same amount of time to get up there as it does to get over to there. So that's the distance the light travels up. And this one right here, the vertical, that's the speed of light up here. This time's different. So we could say T naught, just to represent a difference in the times. That time is shorter down here than this one. It takes less time for that one to go up and down if you were to go straight up and down. So you have a right triangle, you have those distances represented, and all they do now is this. You even have enough math, most of you. You don't realize it. That distance squared plus the up distance squared is the hypotenuse squared. That was our right triangle. Basically, if you remember your algebra, this side squared plus this side squared equals the hypotenuse squared. I won't bore you. It's in your book too if you want to know. But you do the algebra with that and you get a really cool result. It is that the time it takes in the moving reference frame, it looks scary, but it's not, times the original. So the times are no longer the same. They're different by this factor right here. 1 divided by the square root of 1 minus the ship's speed squared divided by the speed of light squared. And this is so important. I won't make you calculate this out, but it has a name. It's called the Lorentz factor. And we can tell this shift in time just by knowing the factor. It's usually represented with the Greek letter gamma. Gamma. So we can just rewrite this as the two times differ by this factor gamma, Lorentz factor. If the Lorentz factor is 1, then they're the same. But this factor will always be greater than 1 or greater, depending on this speed. And that's what we'll do more of later. And you can use this to figure out how the times are different. And the idea is people in motion relative to you, your time that you look at your watch or your clock will be different than the time you think it takes for them to do something by this factor. It's tricky. So, any last minute questions? Yes?
Did you say it'll always be greater than
1 or greater. Yeah, convince yourself. Put it, the fastest you can go is C.
That's what I was going to say.
So if that was C,
Yeah, that's assuming that.
plug it in and see what happens.
That's assuming there's nothing faster
The-
than. I know there's nothing.
That's correct. Nothing with matter can go faster than the speed of light. We'll discuss that more too. Thanks, everybody.